This is the formation of stratospheric ozone. First, we start with two oxygen atoms combined into one molecule called O2. When the sun rays of UVB and UVC hit it, we get the breakdown of this molecule into two oxygen atoms. These get combined with two These get combined with two more oxygen O2 molecules, O2, into ozone, which is O3. This then combines back into the O2 that we had before. Now we have the destruction of stratospheric ozone. This time, since the destruction of stratospheric ozone is a reversible reaction, we also need the sun. Again, but this time we start with that same ozone we made, O3, and when it is hit by the same UV rays, UVB and UVC, it breaks down into two O2 molecules and one oxygen molecule. This is the importance of stratospheric ozone. First of all, through this diagram, you can see that stratospheric ozone protects us. We live down here. That it blocks out the UVA, UVB. It blocks out some UVA, most UVB, and all of UVC. The stratospheric ozone is very important to humans because UVB and UVC are unsafe and high energy electromagnetic waves. They cause skin cancer, cataracts. They can cause suppression of the immune system. So it's important for the stratospheric ozone to help block UVB and UVC when we mainly have sunscreen to protect us from the lower energy UVA. Then we have its effects on plants. UVC and UVB are both very damaging to both plant cells and cause the death of existing plant and algae. This can cause plant cells to decrease in photosynthesis, and the death of plants and algae can destroy food webs when phytoplankton and fish who eat those phytoplanktons can't survive anymore without the nutrients that algae and plants give. This is anthropogenic ozone depletion. First, we start off with a CFC molecule, or a chlorofluorocarbon. This chlorofluorocarbon is reacted with a UVB and UVC rays from the sun and breaks off a Cl or chlorine molecule. This chlorine molecule then reacts with ozone, O3, to break off one oxygen molecule and combine into a molecule of chlorine and oxygen. This leaves this molecule left with as O2. This is fine in the moment until we see that the chlorine, the oxygen molecule, a free oxygen molecule, will combine with the attached oxygen molecule, turning into O2, but then leaving this chlorine to continue to break down other ozone molecules. This process happens again and again. This is natural ozone depletion. First, this happens in the Arctic cold winters because of the special conditions of the atmosphere. Specifically, we need polar stratospheric clouds to form. These clouds are made of water and nitric acid, which is HNO3. These can only form in the negative 100 degrees Fahrenheit, which is why this special condition is extremely necessary. Then, when this is combined with PSCs such as nitrates, chlorine nitrate, which is ClONO3, and hydrochloric acid, which is HCl. From what the previous ozone depletions, you can tell that the chlorine is going to be the issue here. These alone aren't damaging, but when the Arctic spring comes, in the months September to November in the southern hemisphere, we start to see, not winter, spring. We start to see the UV rays from the sun, again UVC and UVB, start to break down these molecules into Cl2. These further break down into individual Cl molecules. Then we repeat the process that was in the anthropogenic ozone depletion, where these Cls begin to attach to ozone molecules, take an oxygen molecule from the ozone, and turn this into O2. Then a free molecule of oxygen comes and combines with this to equal another O2 molecule. This leaves the chlorine free to begin the process again, stealing another O2 molecule, stealing another oxygen molecule to make chlorine oxygen, turning this into O2, and then a free oxygen taking that oxygen from the Cl to form another O2, and then the process repeating over and over again.